Alright guys, we're going to be talking about the domains of composite functions today. And the book says that the domain of f of g of x is all values in the domain of g, such that g of x is in the domain of f. In order to understand that definition there, it might be good to do a quick review of basic compositions and what happens with those basic compositions. Alright, so here are two graphs. We've got f of x and we have g of x. And what I'm going to want to do with these functions is just pick a value of x and then we're going to evaluate the composition. So let's say we want to do f of g of, let's go with 2. Let's do that. Alright, so first you would do the g of 2 portion. So what that essentially is saying, number 1 is you're plugging in the number 2 into function g. So like if you had the equation, 2 of course would be the x value. So on the graph of the function g, we find the x value of 2 and the y value there is 1. So then this would become f of 1. So the key was though that the y value of function g is now becoming the x value of function f. So the y value of g becomes the x value of f. So then you go to function f, you find when x is equal to 1 and then discover that g of x, or that f of 1, is equal to 1. So now let's go back and read that definition. The domain of the composite is all the values that are in the domain of g. And that's because the first value that you're plugging in there, the x values, must be in the domain of g since you're going to evaluate the function g first. But then it says such that g of x is in the domain of f. Well, g of x, or in other words, the y value that we got from function g, must be in the domain of f. Okay, so then what if I wanted to find the domain of this composite function? I would need to read that and I would need to say, okay, if the y values of function g must be in the domain of f, well, the y values of function g are all the values from -3 on up to infinity. Well, unfortunately, function f does not start its domain at -3. Its domain only goes from -2 to 3. So when I look at function g, I can only use the y values that are from -2 to 3. So I'm going to highlight every part of that function whose y values are -2 to +3. So we have this has a -2 y value, and then we're going to go up to 3. And this side also has a piece that's from -2 to 3. And so our domain that we're allowed to have is actually starting at this point and going on this direction until you get to the y value of 3. And we'll just say that that's right there because that's where we have our arrow. And then we can also have then this part that goes along here all the way until we get to the y value of 3. So the final domain is going to be from, it looks like -3 to 1 and 1 to 3. Don't worry, this is tricky. We'll do another example. All right, so here's another example. We have here f of x, which is going to be equal to the square root of x, and we've also got g of x here as well. And I didn't give you an equation for g of x because we are focusing just right now on graphically how do you find the domain of a composite. So once again, in order to find the domain of f of g of x, according to the definition, g of x, or in other words the y values of g, must be in the domain of f of x. So we must look at the domain of f of x. F of x has a domain from 0 to infinity. So if I highlight all the y values on function g that have values of 0 to infinity, I would only be highlighting from 0 and on up. That then indicates that the final domain of our composition is from negative infinity to 1 and from 1 to infinity. And we can include these dots here and here because we are allowed to equal 0. I think on that last example I might have put parentheses, but they should have been brackets. So I hope you guys fix that on your notes. We also want to take a look at these algebraically, and let's see what happens algebraically. Alright, so the last example that we just did was f of x was the square root of x, and actually g of x was 2x squared minus 2. So, remember what we want is to have g of x be in the domain of f of x. So algebraically what that looks like is you would first find the domain of f of x. So step 1, domain of f of x. Well, our domain of f of x is from 0 to infinity, including 0. As an inequality, that would look like x needs to be greater than or equal to 0. And then what we're trying to do is take all the y values of g of x and see that they're in the domain. Well, in a composition, when you're doing f of g of x, this is telling you to take g of x and to plug it in for x, for the f function. Well, g of x, that's 2x squared minus 2, so they're saying plug in for x in f of x. Well, instead of plugging it into the actual function, since we're just talking about the domain, we're going to plug this into the domain. And so then that's going to look like 2x squared minus 2 is going to be greater than or equal to 0. And so if I go ahead and solve this, we've got 2x squared is going to be greater than or equal to 2. Or in other words, x squared needs to be greater than or equal to 1. We have to remember that we're looking for numbers, values of x, that cause the inequality to be greater than or equal to 1. So if I look at a number line, at 1 squared is 1, so it's equal to there. At negative 1, when I square negative 1, I also get 1, so it's equal to there. In order to ensure I get numbers that are greater than 1, I would need something like 2. 2 squared is greater than 1, so we're going to shade this direction on our number line. And then I can also use values like, say, negative 2. Negative 2 squared would then also be 4, which is greater than 1, so I would shade this direction. So my final domain, again, is negative infinity to negative 1 and 1 to infinity, just like it was when we looked at the graphical picture. Alright, I think one more example and maybe you'll be ready to do your own practicing. Okay, so here's our last example. We have f of x and it is equal to 1 over x, which has a nice picture here. It does have a vertical asymptote though at x equals 0 and a horizontal asymptote there at y equals 0. That's important. And then we also have, for g of x, the absolute value of x function. And if we remember that that's our v graph. And let's say I want to find the domain of f of g of x. Alright, so using our description before, we know that g of x must be in the domain of f of x. So we need to find the domain of f of x. In interval notation, it would be negative infinity to 0 and 0 to infinity. If we wanted to look at this in inequality notation, the best thing to say is that it's every value except where x equals 0. So, if I wanted to highlight the y values for g of x that satisfy that, the only thing we can't have is when the y value would equal 0. So I can highlight everything here and everything here. The only exception to the rule is right here at 0. That red dot right there cannot be in our final domain. So, as our final answer here, our domain of f of g of x would be negative infinity to 0 and 0 to infinity. Now, algebraically, f of g of x, that would be f of the absolute value of x. And that then means that we're going to take the absolute value of x and we should plug it in for the x in the domain of f. So if I do that, I'll get the absolute value of x is not allowed to equal 0. Therefore, x cannot equal 0, and that would be the only value that is not included in the domain. So we do get the same answer algebraically as we do graphically. I hope this video helps you. I know I'm not there today, but do the best you can, work together, and help each other.